On number 10, you're asked to solve the following right triangle. When we solve a right triangle, that means we need to find all the missing pieces. If you look at this triangle, we don't know the length of side A, this leg, and we don't know the two angles. So we'll begin by finding the length of side A. Of course, the Pythagorean theorem would work well here. So we have A squared, the leg squared, plus the other leg squared, 5 squared is equal to 12 squared, which means that A is going to equal the square root of 144 minus 25. And if I evaluate that on my calculator, I get, just going to round it to the nearest. It says round side lengths to the nearest hundredth. I get 10.91. 10.91. Please take a moment and check that you're able to enter that correctly and get that value as well. Now we need to find angle A. So we'll find that. And looking at angle A, I know the length of the adjacent side, and I know the length of the hypotenuse. So we're going to go ahead and use the cosine ratio, and I'll write the cosine of angle A is equal to the adjacent side 5 over 12. And I'm trying to find this angle, so I'm going to apply the inverse cosine function to both sides. When I apply the inverse cosine to an acute angle, an angle between 0 and 90 degrees, I get the angle itself. So inverse cosine of the cosine of A is A. That's the left-hand side. On the right-hand side, I need to apply the inverse cosine function also to keep the equation balanced. So it's the inverse cosine of 5/12. And when you evaluate that on your calculator, you should get, and round it to the nearest whole degree, you should get 65 degrees. Let's finally do the same thing for B. When I look at B, I can see that I have the opposite side and, again, the hypotenuse. So this time we're going to use our sine ratio. The sine of angle B is equal to the opposite side 5 divided by 12. And again, we're going to apply the inverse sine function to each side of this equation. The inverse sine of the sine of B is B. And over here I have the inverse sine of 5/12. When I evaluate that, the inverse sine function of 5/12, my calculator says I get 25 degrees when I round it to the nearest whole degree. On number 11, we're also asked to solve another triangle, same thing. And you can see we need to find the length of side C and, again, angle A and angle B. So I'm going to begin by finding C. We know that C squared plus, C is the hypotenuse. Let's get this right. Since C is the hypotenuse, we're going to say 7 squared plus 3 squared is equal to C squared. So you can see here we have 49 plus 9 is equal to C squared. That means if I add the 49 and 9, I get 68 is what C squared is. And then I'm going to go apply the square roots to each side. And we're going to keep the principal, the positive root, because we're talking about the length of a hypotenuse. So we won't look at plus or minus root 68. We'll just look at the positive. And the square root of 68 rounded to the nearest hundredth is 7.62. 7.62 units is what you should have written. Now let's go ahead and do angle A. Angle A, you can see from here we know the opposite side and the adjacent side, so we're going to go and use those, opposite and adjacent, and that would be our tangent ratio. So I write the tangent of angle A is equal to 3/7. Applying the inverse tangent to each side, we get that A is the inverse or the arc tangent of 3/7, and therefore A has to be 23 degrees when I round to the nearest whole degree. Same thing for B. Angle B, you can see here we have our opposite side 7, our adjacent side 3. So we're going to write the tangent of angle B is equal to 7/3. And I apply the inverse function to each side. I get the inverse tangent. I get B equals the inverse tangent of, oops, that's a 1 there, inverse tangent of 7/3. And therefore B, when I round to the nearest whole degree, is 67 degrees. Next, a section of road replaced by Interstate 80 contains large sections of unpaved sand. Interesting, but I don't think we need to know that for the problem. The grade of the road was 19.5%. That's what we do need to know. How many degrees above horizontal is this grade? So if you consider this, the grade, what we're talking about here is, for a grade, essentially it's giving us the vertical rise for every 100 units horizontal change. So let's say that we go 100 meters, we're going to have a 19.5 meter increase right here. And the angle above horizontal is this angle right here that we're looking for. So this is the angle we're seeking, and we know that it's 19 over 100. We have opposite and adjacent, so we'll use our tangent ratio. So I'm going to go ahead and call this A just to write it in the equation. I will say that the tangent of angle A is equal to 19.5 divided by 100, which is 0.195. So A itself is going to be the inverse tangent of 0.195. And when we plug that into our calculator, we see that we are looking here at 11.03 rounded to the nearest hundredth, 11.03 degrees raised. Probably 11 would be a more appropriate rounding for this problem. Last question that we're going to do together is number 13. It says the angle of depression from a hot air balloon to a truck is 39 degrees. All right, so let's say that this is our hot air balloon. Okay, that's it. We'll just hot air balloon, and the angle of depression. It says to it. Oh, if the hot air. Okay, the angle of depression from a hot air balloon to a truck is 39 degrees. So again, angles of depression are measured along horizontal. So if I have this horizontal line here, sorry, it's a bad sketch. The angle of depression is going down from that horizontal. So we're looking at this right here. So here's my angle of depression. It's 39 degrees. And apparently here I see the old truck. I don't know. It's a truck. And trucks have wheels. It says that the altitude of this hot air balloon is 250 feet. So I'm going to go ahead and plop in the altitude here, 250 feet. And the question is, what is the horizontal ground distance from the balloon to the truck? Horizontal ground distance would be measured along this line. So we're basically asked to find what's the length of the green line here. Well, the 39 degrees is not in this right triangle, right? But I could, again, if this is horizontal and it's horizontal with the earth, the earth is flat in here, we could, obviously we're assuming all kinds of things about about the problem. So I'm going to go ahead and say, well, these lines are parallel, so I'm going to put the 39 degrees right here because indeed, when two parallel lines are cut by a transversal, the alternate interior angles are congruent. So what we're looking for is, I'll just label this x, the side that we need to find, and you can see we have the opposite leg, and we're trying to find the adjacent leg, so let's go ahead and write it. It's clearly the tangent ratio. So the tangent of a 39-degree angle is equal to opposite, 250, over adjacent, which is x. I don't know that. My variable's in the denominator, so I'm going to consider this as a proportion, right? And my cross products are equal, so I have 1 times 250, 250 is equal to x times the tangent of 39. Almost done. And then to solve for x, I'm going to divide both sides by the tangent of 39, so 250 divided by the tangent of 39 degrees is what x is. And go ahead and grab your calculator, and when you evaluate this, 250 divided by the tangent of 39, you should get, rounding to the nearest hundredth, 308.72